So this is a video for section 2.4 and 2.5 for Math 2. Alright, so this handout is in the Math 2 documents folder. It's 2 pages. There's for one's going to be for 2.4, one's going to be for 2.5. So the 2.4 notes is going to go onto page 19 of your notebook. 19. Okay, so we're looking at some more theorems. First of all, let's put the title of this section. The title of this section is Parallel and Perpendicular Lines. So we're still talking about parallel lines. We're also going to talk a little bit about perpendicular. We're going to look at two specific theorems that have to do with parallel and perpendicular lines. And then we're going to prove these theorems. Okay, so first one, Theorem 13 says, if two lines are parallel to the same line, then they are parallel to each other. So two lines parallel to the same line. So here we have line A is parallel to a line B. Okay, so that's our first situation. But then line B is also parallel to, so the same line B is also parallel to a line C. So if A and B are parallel and B and C are parallel, then essentially that makes these two also parallel to each other. So A is parallel to C. So you may remember something called the transitive property. This is sort of like a transitive property with parallel stuff. Okay. All right, so on page 18, I want you to write what I'm going to write now, which is the proof for this theorem. Actually, I remember now, it's in your textbook. So let me get that page. Why don't you go get your textbook and we'll meet back here. Yay, magic of technology. Okay, so this is in your textbook on page 94. And this is the proof for the theorem that we were just looking at. So I want to talk about how do you prove a theorem. So looking back up at that theorem, there's a hypothesis and a conclusion because it's an if-then statement, right? So our hypothesis is two lines are parallel to the same line. Now that's how we would say it in words, but we can also say it in symbols like is shown here. And that is what we are going to use as our given, okay, in our proof. This is what we're given. So then we have the conclusion. The conclusion is they are parallel to each other, which is what's right here, and that is going to be what we're trying to prove. So in order to prove a theorem, you must prove the conclusion given the hypothesis. Okay, so they have in this example a paragraph proof that we have to fill in the blanks. If all these blanks were filled in, you'd just have a paragraph. That's why it's called a paragraph proof. So we're just going to fill in the blanks to this. So go ahead and take a minute. I want you to read the proof and then start thinking about what you think goes into these blanks. Okay, I want you to pause the video, give it a shot, and then we'll talk about it. Okay, you ready? Got something? All right, let's give it a shot. So, starting with analyzing what we have here. Now we have different letters than in the example they gave from the proof box there. We have L, K, and M instead of A, B, and C, but it doesn't matter. We have two lines, L and M, that are parallel to the same line, K. So K is representing the line that they are both parallel to. So they're both parallel to K. So L is right here and M is the bottom one. You'll notice that there's also this other line here. This was not part of this wasn't part of the proof or the theorem really, but we need it to prove the theorem. This is known as an auxiliary line. Sometimes auxiliary, I think that's two L's. It's sometimes we need an extra thing here to help us, and what this is it acts as a transversal in this proof. Okay, it doesn't change anything that's given. It's just that's a line that goes through all three and acts as a transversal, and that's going to help us. All right, so we're trying to prove the conclusion of the theorem, which says that L and M are parallel because they're both parallel to K. So when we drew that transversal, we also created three angles, angle 1, 2, and 3. What kind of angles are those? They're corresponding angles, right? Because they're in corresponding positions. Okay, so let's go ahead and read what we have here. Since L is parallel to K, angle 2 is congruent to angle 1. Angle 2 is congruent to angle 1. By the Blinck theorem. Yeah, since L and K are parallel, angle 1 and angle 2 are congruent by the corresponding angles theorem. So that's the missing part of A. We don't have to write the theorem because it's right here. Next sentence. Since M is parallel to K, blank is congruent to blank for the same reason. Well, that would mean angle 1 and angle 3, because those are the angles created by M and K, right? So angle 1 and angle 3. Now these can be reversed, the order does not matter. Then they say, by the transitive property of congruence, angle 2 is congruent to angle 3. That's true, right? We had angle 2 is congruent to angle 1, and now we have that angle 1 is congruent to angle 3, so angle 2 is congruent to angle 3. So we have shown that angle 2 is congruent to angle 3. Okay, if these two angles, 2 and 3, are congruent, then what that means is that these two lines must be parallel. And the reason for that is the converse of the corresponding angles theorem. Remember, the converse of these theorems are going in the direction of saying something is parallel. So if something about some angles, in this case corresponding angles are congruent, then you get parallel lines. If you start with parallel lines and you end up with something about angles, it's not a converse. Okay, so that's the proof for this theorem. All right, back up to your notes. Theorem 14. In a plane, if two lines are perpendicular to the same line, then they are parallel to each other. So this is not like a transversal theorem of perpendicular. It doesn't work. What it's saying is you have two lines, M and N, are both perpendicular to the same line, in this case T. So they're both meeting it at a right angle. So it doesn't make M and N perpendicular to each other, it makes M and N parallel to each other. So for this one, I want to do a flow proof with you to get you guys exposed to flow proofs. And there's room on this page, so we're going to put the flow proof for this one right underneath. Okay, so theorem 14, proof. Again, when you're proving a theorem, you want to start with what you're given. So the given is going to be this part. It's the hypothesis. We're given this, we need to prove that it's going to lead to this. So this is what we're trying to prove. Prove this. Okay? So flow proof, remember, is when you have little bubbles or rectangles or boxes or whatever you want to call them. And that's where you put your statements, and then the reasons go underneath, and then there's arrows connecting things. Okay, so we're going to start with one of the givens, which is m is perpendicular to t. So I'm going to put that in a box, and the reason that's true is it is given. Actually, I should write out what the proof wants. Given m is perpendicular to t and n is perpendicular to t, prove that m is parallel to n. Okay, this is important. All right, so then what does that lead us to say? Well, it leads us to say that this is a right angle. So I need a name for that, so I'm going to call that angle 1. And so angle 1 is going to be a right angle. And the reason for that is definition of perpendicular lines. By the way, I'm not going to go over it, but I did create a list of reasons for proof that you're going to want to put in your notebook. And I believe they go on the previous 2 pages in your notebook. We're starting on 19, so they go on 17 and no 16 and 17. Okay. All right, and so that definition of perpendicular lines is a reason that's on that list. All right, so we had another given. We had that n is perpendicular to t. Given. That leads us to saying this other angle down here is a right angle. So I'm going to call that angle 2. So angle 2 is a right angle. For the same reason, definition of perpendicular lines. Okay, now if you have 2 right angles, then they're going to be congruent to each other, right? So on that list of reasons, you'll find this one that says if you have two right angles, then those angles are congruent, and that's called the right angles congruence theorem. Although your book, I don't think they called it that specifically. Instead of calling it right angles congruence theorem, you can just write out the phrase all right angles are congruent, and that would mean the same thing. All right, so we have proven that this angle here and this angle here are congruent to each other. Those are, again, corresponding angles. And corresponding angles should be, if they're congruent, that means that these 2 lines must be parallel. So, similar to the end of the last proof that we were doing, right? We had the converse of the corresponding angles theorem. We have it again. So this time we're saying that m is parallel to n by the converse of the corresponding angles theorem. Okay, and now we have proven it. Yay! Okay, let's go ahead and take a look at 2.5, and I'm only going to introduce you to 2.5. I'm going to extend the due date for the homework for 2.5, but I just want to get you guys started on 2.5. So the second page of the notes says 2.5 notes. So this is going on to page, let's see, that one was on 19. This one's on 19, so this one's going to be on 21. Okay, so 2.5 is on parallel lines, but we're looking at parallel lines and how they relate to triangles. So parallel lines and triangles. Okay, so to begin this one, we have a postulate. It's the parallel postulate. And it says, through a point not on a line, there is one and only line parallel to a given line. So the given line is this one L. And we have a point not on the line. Okay, a point not on the line, that's P. So the question is, how many lines are parallel to this line and go through this point? And there's only one. There's one and only one. Okay, that's what this postulate is saying. And that relates to how we're going to do a little investigation for triangles. Okay, so this is a triangle. I have faith that you know what a triangle is, right? So, triangle, you name a triangle with a little triangle symbol and you write the vertices, which are these points right here, A, B, C, and it doesn't really matter the order as long as it goes around, and you can start anywhere. I could call it triangle BAC, triangle CBA. It's all the same triangle, okay? So we're looking at this triangle and we want to know what is true about these three angles: angle 1, angle 2, and angle 3. So you see there's an auxiliary line here, this extra line. This is where the parallel postulate comes in. This line is parallel to this line, which is the line that goes through the bottom side, and it goes through this point. And there is only one line like that that exists, right? That's the parallel postulate. Okay, so why do we create a parallel line here? Well, once you have parallel lines, then you can start thinking about transversals and alternate interior and corresponding and alternate exterior and same side interior, and all that stuff comes into play now. In fact, here we have a lovely transversal. Okay, so we're investigating the following question. What does the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3 equal? Well, I didn't tell you anything about any measures. This is just, and this could be any triangle in the world. And what we're going to learn right now is true about any triangle in the world. Okay? So, now that we have a transversal in place here, we're going to use the fact that we have a transversal and we have parallel lines. So we have this angle 3 here. 3 has another angle that is going to match up with it so that it's an alternate interior pair that would be congruent to it, and that's this one. So this one right here and this one right here are alternate interior angles. And because those lines are parallel, they'll be congruent. So I'm just going to rename this 3. Okay, I'm just going to call that angle 3 because they're the same measurement, right? Okay, so then let's do the same thing for angle 2. Here's angle 2. And we have another transversal over here, right? We have this transversal right here. So now we can use the fact that this angle right here, angle 2, and this angle right here are alternate interior. So they would be congruent to each other. So I'm just going to rename this angle right here angle 2. So remember what our question is. What do these three angles add up to? Okay, well, if we take a look at here to here, this is what we're adding all up. What do those three things add up to? The answer is 180 degrees, because this is a straight angle, right? A straight line is always 180 degrees as an angle. So there's our answer. Okay, this is called, and we're going to write this underneath, the triangle angle sum theorem. which says the sum of the measures of the interior angles of a triangle is 180 degrees. Okay, we're going to do some examples of this next week. Alrighty, I'll see you guys next week.